Thank you. Questions? Thanks for getting quiet so fast. Evidently the gravity of matrices and three-dimensional graphics from by hand makes you all go, wow, I'm going to be quiet. Or better yet, you're just like, let's get this over with. What do you think? Questions on what I've just talked about? Anybody? So does it blow your mind that you cannot discern direct effects from indirect effects between any two variables in the path analysis? It's pretty ridiculous, huh? The same thing is going to show up in factor analysis, but in different ways. We get up against the mathematics of things, so our research design has to kind of be built around what we can and we can't identify or mathematically test. So testing hypotheses can only be done up until a point, and that's the point right there for you. So if you ever review a paper that you absolutely hate in using mediation, if you're the reviewer of it, go ahead and say, that's not true, it's this. And the author cannot go and disprove it. Right? How do you like that for science? Science! We're killing it. Okay. So, part of the reason why, for all this, when we say these models are all the same, comes from the direct specification of the algebra that underlies this. And one of the things that we do in path analysis is we go and, I didn't even mean to do that, wow. We go and we specify our path analysis, we estimate it, and we check for model fit. Right. And that model fit, we have all these methods and metrics of it. But if the model doesn't fit, one thing that we do to look at is to see whether or not our model implied covariance matrix is different from a saturated model, where everything is unstructured itself. Right? Is that, remember, the command residual? I think we did this in the homework. We had to spit out the residual covariance matrix, and it gave you this matrix, and you had to pick out the two, and those are the places where your model is the most off. Now this model, with three variables, let me ask you, is this a saturated model? How would we know? We know through identification or counting. Counting parameters. Now in my slides I realize I didn't do a good job in differentiating what we need to count. Well, let's go back and try to do this ourselves. If we have three variables here. We have two endogenous and one exogenous. But let's imagine we put all three together and we want to put them into an analysis where we use a likelihood for all of them. So now we have a three-dimensional multivariate normal distribution that would be the saturated model for it, right? With three variables. This is endo plus exo, exogenous plus endogenous. We have, I cannot spell, a saturated multivariate normal with how many parameters? 6. Let's see here. The mean vector has how many parameters? 3 means. The covariance matrix has how many parameters? 3 variances, 3 covariances. Right? So our overall saturated model would look like this. If we were to take our variable x, our variable y, our variable z, put them into this vector, we would say it follows a multivariate normal distribution. The mean vector itself would be x bar, y bar, and z bar. And the covariance matrix would be sigma squared x, sigma squared y, sigma squared z, sigma xy, sigma xz, sigma yz. Right? And so all these three things are repeated on the top, right? Sigma xz, sigma yz. So there we have now. So total, if we add all these together, this equals 9 parameters. And part of my slides say count all of them. So if we have 9 parameters, this is 9 is our 9 is like what the saturated model does. So we know that our model, to be just identified, can only have 9 parameters estimated. Right? Just identified means we have perfect model fit. To be over-identified would be to say that our model would have fewer than 9 parameters. And model fit would be therefore be something that we have to we could evaluate. Right? To be under-identified would be to come up with a model with 10 or more parameters, something that we had too many. Right? So how many parameters do we have in our model? Let me count the parameters here. Right? There's 1 for beta 0y, 2 for beta xy, 3 is beta 0z, 4 is beta yz, and 5 is beta xz. 1, 2, 3, 4, 5. Okay. We have 4 left. 6. Parameter number 6 is sigma squared error for y. 7. Parameter number 7 is sigma squared error for z. And we have 2 left. What are the 2 left for us? It's getting quiet. Well, because we're including x as an exogenous variable, we need the 2 distribution terms that describe it. So we will estimate for x, we'll estimate, essentially it's like saying this is our model, x equals beta 0 x plus error. There's an saturated model for x. I'm sorry, not saturated, an empty model for x right here. Right? So in our empty model for x, there is model parameter number 8 right here, beta 0 for x. And then along those lines, we'd say error for x follows a normal distribution with a mean 0 and a variance sigma squared x. I don't put an error there because it's not residual, right? It's just x. It's an empty model. It's an odd distinction. It's still variance. It still functions the same, but it's not being described. It's the variance of x, period. But this right here would be the 9th parameter itself. So our model is over, under, or just identified. You remember the rule? Just identified is where they're equal, right? Just identified. So why we describe it that way is conceptually the following. Yes, Jen. Yeah. Mm-hmm. That's it, exactly. And this is where I didn't do a good job in my slides, but let me try to describe it. There are, and actually this also stems from the books, the chapters you're reading. It's sort of mixed. If you read one chapter, it may say count everything, and you read another one, or you read the bulk of books that were written before 1995, and they say count only the covariance matrix. And the reason is, let me get to that. If I don't get to that in 5 minutes, raise your hand, please. Okay, so she's my 5-minute timer. Cool. Or someone else help Jen out. But here, let me describe this. What the reasoning for just identified happens to be. So what just identified means is if we could go and take all of these parameters right here in our saturated model, all 9 of those, and set them equal to our model parameters, right, we would have a series of equations that we'd have to solve. Right? So if we were to say, how do we find x bar, or how do we find y bar, and how do we find z bar, right? And we'd also have sigma squared x, we'd have sigma squared y, we'd have sigma squared z. I'm doing this kind of on purpose to be a little explicit. Sigma xy, sigma xz, sigma yz, right? So essentially those 9 parameters right there, if we were to do a saturated model, they contain all the numbers that our path analysis parameters come from. Right? So we have 9 equations, and we have 9 unknowns in our analysis. Right? So our analysis cannot have more. If you remember in algebra class, you ever done a system of equations before? You try to usually have a series of equations, you have a series of unknowns, and you have to solve one of them and then back substitute and so forth. Right? Our process is the same, actually, to figure out why just identified is just identified. We can't have more parameters than there are things to figure out. Right? So now I'm going to get to. So why we sometimes count some and sometimes count the other, I'm going to take these equations and break them into segments. Right? This is for the mean vector, and this is for the covariance matrix. So in our counting, a lot of times, and in some of my slides, we only count the covariance, and sometimes we go and count the mean vector plus the covariance. And the reason for that is the following. The terms, our model parameters that contribute to the covariance matrix are the following. And I'll show you why after I get here. This is where we're going to get into a little bit more linear algebra. All the slopes. So the slopes are beta y for x, beta z for x, and beta z for y. The residual variance, cannot write and spell. Residual variances, right? So we have sigma squared e for y, we have sigma squared e for z. So all of a sudden, this covariance matrix has 6 parameters to it, and there's 5 of them that show up there. The slopes, the residual variances, the residual covariances, which we don't have any. Right? So I'm just going to put a big fat 0 / here. And then we have the exogenous variances. Right? So that was sigma squared x. So there's our 6th term. And then finally our exogenous covariances, which we don't have any. So sometimes what you end up seeing is a kind of a modified version of counting. Because if you count only the covariance parameters, then you only count, if you want to do the T rule with it, you essentially say, well, then I'm only going to count the slopes, the residual variances, the residual covariances, and then the same thing for the exogenous variances and covariances. So we'd have 6 parameters and 6 unknowns. Now, why that is the case is the side for the mean vector contains everything else. And almost always in a path analysis, it's saturated. Right? So our 3 terms for the mean vector, our mean vector gets figured out, well, the 3 terms that people equate it to. This is not precise, and I can show you algebraically this is not precise, but once you've figured out these 6 things, they sort of factor into the mean vector. But our 3 terms up here are beta 0, are our intercepts. So these are the endogenous variables. To have an intercept, you have to be an endogenous variable. And then our exogenous variable means. Right, so this is x bar, and then beta 0 y and beta 0 x. So why sometimes we neglect to count the mean vector is that it's pretty much always saturated. We always have the number of terms equal to the number of possible terms in it. In a factor analysis, when we get to this, when we talked about a little bit last week, our mean vector still shows up, but we give every item a mean of itself. So it's still saturated there. So a lot of times people shortcut this, cut out the mean vector, and say the only place where we're going to be off is this covariance matrix. So I need to count the covariance matrix terms and then count my model parameters for it. So I'm caught in the middle, and then my slides reflect it, and I apologize to you for that. I'm caught because a lot of common thinking still just counts the covariance, but to be precise, we should count everything. Right? Everything's going to contribute to a likelihood. Everything will go into this model fit function. And especially when you look at path analysis in the context of linear models, we do everything with it. But why we haven't counted it for a number of years is just because the covariance matrix is the place where it decides. Does that help answer your question? So, but to see this, you've got to remember, okay, I'm counting the covariance, counting the covariances. Oh, I need to count up all these other terms too, slopes, residual variances, and so forth, right? And that seems very highly specific. Right? Actually, the path analysis model, the path diagram itself, especially when we add in the error terms for each of these, like we have a little error, a little error, a little error right here, tries to represent that. We have 6 paths, essentially, in this path diagram. So the path diagrams are built off of the covariance matrix itself. A long time ago, when we weren't as concerned with the mean vector, estimation with maximum likelihood, you didn't have to give it all of your data. You could give it a summary of your data. You can give it your data's covariance matrix. And it would try to figure out the slopes and variances based on something called an inverse Wishart distribution, likelihood, to match it to what you did. And that is sometimes called limited information estimation, whereas our process these days uses something called full information estimation. Have you heard the word full information before? FIML, full information maximum likelihood. Right? So in full information, we need everything. In limited information, it's basically saying we're going to take the covariance matrix and run with it. So this is kind of the standard. We're moving towards full information. If you have a data set that's complete, you have no missing data, and everything is completely multivariate normal, then the use of full information and the use of limited information give you identical results for maximum likelihood. How many times do you have missing data? Right? You have one piece of missing data, they're not going to be identical. Or if you're not fully multivariate normal, they're not going to be identical. So those are 2 cases for it. Full information maximum likelihood is much more flexible than the limited information version of it. But the bigger question is, why are these terms over in the covariance matrix? And why are these specifically there? That's weird, right? Anyone want to know? No. Who would not care? So the reason for that comes from the algebra behind what we're doing. Our algebra, if we go to our Dropbox folder, I just dropped this. I thought I gave you a chapter before to read that describes it in a little bit more detail. I'm going to describe this, the Kaplan Chapter 2 version of it, and you can totally see it. Let me go back and open that on my desktop. The Kaplan chapter, that one, for path analysis describes this a little bit. This gets into the idea of each model that we specify implies a covariance matrix. Right? So we put this model together, and now because of this model, we have this model implied covariance matrix, and we're going to compare it to our saturated matrix right here. Now this gets really ugly real quick, though. This is why I didn't teach that in this class. I tried to get away without it, but I really probably should have kept teaching it. If you go and specify your path analysis in matrices that look like that, ugh, that's nasty. Y, I can't draw on this either. It's a shame. Y here is your vector of observations. So let me just try to specify this real quick. Right, so we're going to say the vector Y is equal to this vector alpha plus this matrix beta times Y. What? Y equals Y? Doesn't that seem weird? I could never get past that before. Plus this vector gamma times the vector X plus E. Or this is not E, they call it, is that Xi? Squiggle. Okay. So when you put all your path analysis matrix, that would be like us saying the following. Let's take X, Y, and Z. Now X is exogenous, right? Which means we're not predicting it, but we have to put it in this analysis to compare it with our three-dimensional multivariate normal. So I'm going to put it in there just as is. It's going to look like the following here. Alpha is where our beta zeros go. Beta 0 X, beta 0 Y, beta 0 Z. Right? That is our vector that holds all of our intercepts. Beta, so this is alpha, right here, is a matrix. Now, it's hard to describe what it's multiplying, but it's multiplying Y itself. Right? So if Y is X, Y, and Z, we can put X, Y, and Z right in that matrix itself. Right? That's just the matrix that holds our dependent variables. And what it shows up in beta is the beta weight for each one of those variables in the regression line for it. Right? So for X, when we go back up here, we've got to go back to our regression line. Here are our regression lines. For X, we don't have any predictors of it. So it's actually going to have a series of zeros. Right, so this will be 0, 0, 0. So these zeros will multiply X, Y, and Z, and we're not going to get anything out of that matrix product to predict the line for X. For Y, what is predicting Y? Well, X is predicting Y. And because X is in the first spot, we're actually going to have the slope for Y from X in its corresponding row in that first spot. But Y does not predict itself. Z does not predict itself. And finally, for Z, I'm going to go with the original model where we had that mediation diagram that we had talked about before. What is predicting Z? X is predicting Z. Y is predicting Z. But Z does not predict itself. So what this matrix beta is holding are some of our slopes. These are the slopes. Slopes. Actually, it's all of our slopes here. Of endogenous onto endogenous. Now, this is a little weird. X itself, X is an exogenous variable, but because we put it in the likelihood, it shows up in this matrix. If we didn't put it in the likelihood, it would be off on its side. So gamma, then, if I do this gamma matrix, if we don't actually have any more variables to multiply it. This little X bar, this is purely exogenous. This is purely outside of the likelihood itself. So we don't actually have any variables to put in there. Go figure. Now I'm feeling a little messed up. There's different ways of thinking of this. Let me back up. I'm going to take X out of here. I'm going to take X out of this thing. We'll just have this be 2 by 2 right here. Kaplan does it this way. You can do it either way here. So there. Our prediction doesn't have X. Okay? There. That's what we look like. Oh, no. Please. Oh, OneNote, you're killing me today. My God, I try to depend on you. Well, there seems to be a problem.
SEM class rectorate asterisk.
Yeah.
Microsoft OneNote dialog.
Yep.
Recover copy button. Alt+C. Items.
That's it exactly.
SEM class rectorate asterisk.
Being
OneNote window. Items.
Previous equations. Where do you left?
Start. Selected. Requires selection contain. Items. Items. Items.
the variance for x, it's like thinking x
Items.
is, there's two ways of looking at it. They're equivalent. I put x in this line,
SEM class rectorate asterisk. OneNote window.
and
editing,
I'd said, oh,
editing,
this is, it's
editing
endogenous.
text.
It's like endogenous, it's like we're predicting it by itself. But really, it's just, when it's exogenous, it's just by itself. And we just estimate its mean to be its mean, and its variance to be its variance. What I was trying to draw down here would have given you that same result.
Items.
But that's it. Am I doing something wrong with this? You guys seem to know. What's that? Seriously,
Start.
like, no, it's like
Selected.
I'm
Start.
not
Selected.
phobic when it
Start
comes
menu.
to this stuff, but it's
Pane.
drawing boxes
Desktop.
now. that I have
Launch
no idea where it's
desktop.
from.
Non-selected.
It's killing me.
Draggable. Column 1, row
All right,
1.
let's try Word. Okay, so let's go back to this here. Let's say that y.
Document 1. Word window.
Is it my ink
Document
tool?
1.
Okay, y. This is equal to alpha plus beta y plus gamma x plus this error term right here. All right, so y, I'm only going to put endogenous variables back in y. So why we see y on either side here, y and y, is because sometimes in the path analysis, endogenous variables will predict other endogenous variables, and that's where that matrix beta shows up. Right? So here we have y and z. We put our endogenous variable beta 0 for y, beta 0 for z. We put our beta matrix. We put y and z. We have the. We do not have anything for y does not predict y. Z does not predict z y. So there's zeros in that. Y predicts z though. So this is beta z of y, but z does not predict z. Right. So this right here is beta. This is alpha. This is y. Now we need gamma x. So x is our one exogenous variable, x by itself, and gamma is the series of effects that it needs to be to multiply it. This is a 1 by 1, so this needs to be a 2 by 1 vector. All right, so what we end up here is each time that x goes on predicts y or z, we get its effect in it. Beta for y of x, beta for z of x. And then finally, we have our error terms. The error for y, the error for z. So if we put all those in the boxes that look like that, what we can get from algebra
Kaplan, page
is
down.
to figure out what we need to do to say what does that model imply for the covariance matrix. We can look at the following equation here. Well, this is a little weird, but I mentioned on one of the classes where we talked about the expected value. And expected value is a mathematical function that takes your model and tries to map it onto a distribution that's mean. But expected value also gives us a covariance. It's a special type of expectation. This is telling us what our model expects the covariance to look like. So if we truly knew all the regression slopes, right, if we had the right answer for all of them, our model would have this covariance. That's what it says. And here is the math behind it. So I don't need you to know all of this off the top of your head. I don't know it off the top of my head. But what this section is doing is it's saying this top quadrant right here, if we look at our covariance matrix, this is the covariance matrix of our endogenous variables with our other endogenous variables. Right, so that top quadrant,
Running programs.
mapping it on to
Page 1
Word
content. Read only double tap to place
That top
text
quadrant
insertion
would look
point.
like
Triple
this.
tap to
If
enter
we say
selection
the
mode.
sigma that it's talking about, this would be like saying this is with y and z up here, and then x down there. So y and z is the portion of the covariance matrix that comes
Kaplan,
from all those nasty
2009,
matrices. Right
Chapter 2.pdf.
But take
Adobe
a look at what
Acrobat
terms
Pro
are in those
window
matrices.
of
We've got
page
the
view.
things in beta,
Pane.
the things in gamma, the things in phi. We didn't even talk about phi. And the things in psi. So beta, we know beta is our vector of regression coefficients of endogenous variables on endogenous covariates, slopes. Gamma are the slopes that come from exogenous variables predicting endogenous variables. Right? Phi is the covariance matrix of all the endogenous variables. It's just their estimated variances. So for us, that's just X's variance, that thing. It's saturated. It's perfect. It fits perfectly. And then finally, this psi matrix here is the matrix of residual variances for each of the endogenous variables. So in this portion of the covariance matrix, the only parameters that show up are from that list I gave you. Slopes for endogenous variables, variances of endogenous variables, or residual variance of endogenous variables, residual covariances of endogenous variables. What else here? Variances and covariances of our exogenous variables. So that's the top portion. The bottom portion has that phi matrix. It's the variances and covariances of exogenous variables in it. So what the math works out to do is to say, this is a long diversion from where I was really trying to go with this, which was by math, that's the only terms that show up in the covariance matrix. But if we know these terms exactly, we can actually build a covariance matrix from what we do. We could actually build a mean vector as well. So, questions? Yes.
Why is it organized this way? You explain every element. Why is it organized this way?
Why is it organized that way? In terms of broken down to each of these sections?
Let's see. So this one.
This right here. So the matrix products, the math works out to be specific things depending on what's in each area of the covariance matrix, mathematically. So if you want to go back to the regression line itself, that regression line that we have in matrices right here, this thing, is in terms of y. So if we take its covariance of y with y itself, it would be the covariance of this line. And that's why that shows up in that top quadrant. It's what we do with x that starts to mess things up, that shows up below. Does that help? Not really. Do you have, what can I do to better describe it for you? Other questions? Okay. Well, here let me go a step further. This is dangerous. Should I go a step further? You want to go a step further? Let's take our hypothetical path analysis. And using R, let's build this covariance matrix so you can see what happens when we say certain paths are there or aren't, because this might help you understand what is happening with residual covariances, with not residual covariances, and why, for instance, when we do the residual statement and we get a comparison between what our model is predicting from what the saturated model says, why we add some things and not others. Does that sound okay? Or are we off on a tangent? I'll do it. We'll see how this turns out.
Running programs.
Okay, so I'm going to go to
Studio
R,
window.
and we're going to create each of these things, right? We're going to create a matrix alpha.
A. Project window.
I can't
Selected.
create it
Close button. Double tap to activate. Windows.
Oh boy.
Windows sign in. Pane.
This is interesting. No, that's okay. I'm having technical difficulties. Can you give me a second? I'm going to stop this here.